This presentation is the total synthesis of strychnine. My name is John Eberts, and my current credential is a Bachelor of Science in Chemical Engineering, but I'm a master's candidate, as we all are, at University of St. Joseph. Strychnine is a powerful poison used today to kill rats. It was first isolated from the strychnose family of plants by Peltier and Caventour in 1918. It's very complex for its size. It has 7 rings, which makes it interesting to organic chemists. It was first synthesized by Woodward in 1954, and we'll review his process. Then an enantiomerically pure compound was synthesized by Shibasaki in 2002. The Woodward paper actually predates the use of the retrosynthetic approach, so this retrosynthesis was deduced from the forward synthesis that was in the paper. Woodward started with a racemic mixture, so stereochemistry was not important. He proceeded by forming ring B first, then C, E, D, and G. He actually maintained the rings from the starting materials with rings A and F. Since Shibasaki was going for a pure enantiomer of strychnine, his task was a little more difficult. The main difference in his approach than Woodward's is the order of ring formation. He formed A and then a B and D together, then C, G, and F. Tandem cyclization was used to form the B and D rings together. He maintained ring E from his starting materials. With that overview in mind, we'll look at the synthetic strategies of both Woodward and Shibasaki. Woodward started his synthesis with the formation of ring B. To do this, he used acetoveretrone and phenylhydrazine. Through this, he also brought in rings F and A. The reagents were polyphosphoric acid, formaldehyde, and dimethylamine. The primary mechanism is that the primary amine nucleophilically attacked the carbonyl, then cyclization occurred around the secondary amine to form ring B. Woodward next formed ring C using pyridine and toluene sulfonyl chloride. The pyridine created the 5-sided ring C, and the toluene sulfonyl chloride protected the secondary amine. You'll also see that the ester was maintained and the double bond in ring B shifted, creating a tertiary amine. Next, we'll look at the interesting reconfiguration of ring F that was brought in through acetoveretrone. The first step was to ozonate the original ring F to break it apart. Hydrolysis, reesterification, and acetylation were then used to reform the ring in a separate position. You'll also see that on ring C, the toluene sulfonyl group was removed so that the acetylization could occur on that nitrogen, and the ester has been changed from having an ethyl group to having a methyl group. To form ring E, Woodward used methanolic sodium and sodium methoxide. In this reaction, the 2 ester groups cyclized, forming a 6-ring ring E with 2 double bonds, and a hydroxy group while maintaining one of the esters. Woodward next formed ring D by using selenium dioxide and ethanol. This reaction is interesting in that the acetyl group cyclizes all the way around to the secondary amine. An additional carbonyl group is gained from the selenium dioxide. Finally, ring G is formed using ethanolic potash. This involves cyclization at the hydroxy group. In total, Woodward used 25 steps to form the racemic mixture of strychnine. Shibasaki's synthetic strategy began with the addition to ring E from the cyclohexanone. This addition of the dimethylmalonate was done with an asymmetric Michael reaction that was catalyzed by aluminum lithium bis binaphthoxide complex, ALB. It's interesting that this ALB complex was reported on earlier by Shibasaki in 1998. Thus, they were able to apply it to this reaction. You'll note that Shibasaki started with simpler starting materials than Woodward, And they also were able to immediately establish an enantiomerically pure compound, which they could carry through the rest of the reaction. This strategy was undoubtedly due to their knowledge of the ALB complex and its use in the reaction. Next, Shibazaki created ring A and prepared for the tandem cyclization reaction. Ring A was actually brought in from 1-iodo-2-trimethylstanylbenzene, and it was added to ring E. To prepare for the tandem cyclization, the TIPS protecting group was removed and an SEM protecting group was added. One of the keys to Shibazaki's reaction is the tandem cyclization to form rings B and D at the same time. They first used 2,2-bis-ethylthioethane-1-amine to replace the hydroxy group. They were not sure about the mechanism for the actual tandem cyclization, but they speculated that it started with the reduction of the nitro group with zinc, then a 1,4 addition of the secondary amine, and indole formation. Formation of ring C was done through the cyclization of one of the thioethers that was shown on the previous slide. They used MS4A to reduce the side reactions, and also added titanium chloride before adding the sodium cyanoborohydride to prevent ring openings. Shibazaki had to go through quite a complicated process to form ring G. It started with the removal of the SEM protecting group, then acetylation of the nitrogen in ring B, then replacement of the PMB protecting group with a TIPS protecting group, then reduction of the remaining thioether with nickel boride instead of Rainy nickel, which was used by Woodward in his process, and finally cyclization at the hydroxy group. Finally, Shibazaki formed ring F through removal of the acetyl group and the use of malonic acid. His process also involved 25 steps, but you have seen that it is quite a bit more complicated than Woodward's. So they basically used the tandem cyclization to balance out the steps that were added by all the protecting groups. Woodward really only used one protecting group, the toluene sulfonyl group. He added it when he added the pyridine, and it protects the pyridine nitrogen during the manipulation of the other nitrogen in the compound. Woodward removed the toluene sulfonyl group with hydrochloric acid at the same time he reconfigured ring F. Shibazaki's first protecting group was on the carbonyl using an acetal. This addition was catalyzed by tocilic acid. The acetal was removed with camphor sulfonic acid, CSA. As we saw in the discussion of his synthetic strategy, Shibazaki also used a number of protecting groups for the hydroxy groups in his reaction. He used paramethoxybenzyl, PMB, trimethylsilylethoxymethyl, SEM, and trimethylsilyl, TIPS, or TIPS. You can see here that these protecting groups were used in 3 different hydroxy positions. Shibazaki removed the protecting groups and the hydroxy groups in various ways throughout the synthesis. He removed the SEM with hydrochloric acid. He actually replaced PMB with TIPS. He then removed the TIPS with sulfur trioxide pyridine, triethylamine, and DMSO. One of the interesting mechanisms that was included in these 2 syntheses was Woodward's ozonation to open the ring that was originally brought in as part of the acetoveratone starting material. This reaction is done at minus 78 degrees Celsius to avoid side reactions, and the first result is the formation of a primary ozonide. This is a 5-sided ring that is unstable, so it rearranges to another ozonide through an intermediate that has double bonds on 2 of the 3 oxygens. This second ozonide is more stable than the first because it only has 2 oxygens bonded together. This second ozonide is then reduced with DMF to complete the reaction. There are several lessons to be learned from the review of these 2 syntheses of strychnine. First, one compound can keep organic chemists busy for over 50 years, which is an amazing thought. And modern synthesis articles are easier to interpret than old synthesis articles that do not include retrosynthesis. Protecting groups cause an increase in the number of reactions, which isn't surprising, and combining steps reduces the number of overall reactions, which was a point emphasized by Hayashi in his article Time Economy and Total Synthesis. The other lesson learned is that ozonation is a cool reaction. This is a list of references that was used for this presentation. Thank you for your attention.